The most dangerous earthquake clock in North America right now is not the one you have been told to watch. It is not the stretch of the San Andreas that runs past Los Angeles. It is not Yellowstone. It is a 600-mile crack in the seafloor off the Pacific coast, and the piece of it that concerns seismologists most is not the famous northern end near Seattle and Portland. It is the southern end, the quiet end. The lightly populated, lightly instrumented stretch off Northern California and Southern Oregon that almost nobody talks about. The Cascadia Subduction Zone last ruptured along its full length on January 26, 1700, in an earthquake now estimated between magnitude 8.7 and 9.2. 326 years have passed since then. And this year, researchers publishing in the journal Science Advances took autonomous underwater vehicles and remotely operated submersibles down to the seafloor to re-examine the sediment record at one of the most important paleoseismic sites on the entire margin. What that record appears to show is that the southern portion of this fault does not wait 500 years between earthquakes. It may wait closer to 220. Today we are going to break down exactly what is going on, where it is most dangerous, and whether things could get even worse. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally felt an earthquake strong enough that you had to grab onto something to stay upright? Tell me where you were and what it felt like. If you want to be the first to know every time something major happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one so the algorithm actually shows it to people who need to see it. By the time we are done here, you will understand exactly why the number 9.1 is both real and misleading, and why the earthquake that is statistically closest is not the one almost anyone on that coast is preparing for. Now let us get into it. For most of the 20th century, the Pacific Northwest was considered seismically boring. That is not an exaggeration. Geologists looked at the coast from Cape Mendocino in Northern California up past Vancouver Island and saw a subduction zone that was doing nothing. No great earthquakes in the historical record, no offshore ruptures, a rare, quiet gap in the Ring of Fire where, as far as anyone could tell, the big one simply did not happen. Building codes in Seattle and Portland were written on that assumption. That changed fast. In the 1980s, a geologist named Brian Atwater began digging in the tidal marshes of Willapa Bay in Washington and found something that did not belong. Layers of dead forest soil buried under marine sand and mud. Whole stands of red cedar that had been standing on dry ground one moment and drowned in salt water the next. The land had not sunk slowly, it had dropped. That is the fingerprint of a great subduction earthquake, where a coastline that has been squeezed upward for centuries suddenly falls several feet in the space of a few minutes. Then came the date. Tree ring analysis on those drowned cedars showed they died between the growing seasons of 1699 and 1700. And in Japan, across 5,000 miles of open Pacific, historical records described a tsunami that struck the coast on a January night in 1700 with no earthquake felt beforehand. The Japanese called it an orphan tsunami, a wave with no parent. Working backwards from the arrival times at multiple Japanese ports, scientists were able to place the earthquake at roughly 9 o'clock in the evening local time on January 26, 1700, and to estimate its size from the height of the wave that crossed an entire ocean. That is where the magnitude range of 8.7 to 9.2 comes from. But one earthquake is not a pattern. To get a pattern, you have to go offshore, and that is where the real detective work happened. In 1990, a scientist named John Adams noticed something odd in sediment cores pulled from the deep submarine canyons off Oregon. Layered through the fine ocean mud were coarse, sandy beds that did not belong there, deposits laid down by underwater landslides called turbidites, and they had a marker. Roughly 7,700 years ago, Mount Mazama in Oregon erupted and collapsed into what is now Crater Lake, dusting the entire region in a distinctive volcanic ash. Above that ash layer, in canyon after canyon, Adams counted 13 turbidites, the same 13, in channels separated by hundreds of miles. That was the moment the picture changed, because sediment does not slide down 13 separate submarine canyons at exactly the same 13 moments by coincidence. Something was shaking the entire margin at once. Beginning in 1999, Chris Goldfinger of Oregon State University and his team started running research cruises to test that idea properly. Over more than 2 decades, they collected piston cores, gravity cores, and box cores up and down the margin, dated them with radiocarbon, and correlated the layers site to site. The record they built now stretches back 10,000 years and is considered one of the longest continuous earthquake histories anywhere on Earth. It contains 41 separate events. And here's the part nobody expected. Those 41 events are not all the same earthquake. 19 to 20 of them are full-length or nearly full-length ruptures, the entire 600 to 700 miles of fault letting go at once, the magnitude 9 class event. But roughly 22 of them are something different, thinner beds, restricted to a shorter stretch of the margin. present in the cores off southern Oregon and northern California, and absent in the cores off Washington. Partial ruptures. And when you count only those southern events, the average interval between them drops from about 500 years to roughly 240. At the very southernmost end, some estimates put it as low as 220. To put those numbers in context, it has now been 326 years since 1700. So before we go further, we need to be precise about what a turbidite actually is and why anyone trusts it as an earthquake record, because this is the hinge the entire story turns on. Picture the edge of the continental shelf offshore. Fine sediment washes off the land, drifts out over the shelf, and settles on steep underwater slopes at the heads of submarine canyons. It piles up there for centuries, held in place by nothing more than friction and its own weight. Then the ground shakes. Everything on those slopes lets go at once and pours down the canyon as a dense underwater avalanche, a slurry of sand and mud moving fast enough to travel tens of miles across the abyssal plain. When it finally slows, it settles out. Coarse grains first, fine grains last, leaving a single graded bed with a sharp bottom and a gradual top. That is a turbidite. Between events, ordinary ocean mud drifts down at a slow, fairly steady rate, forming what geologists call hemipelagic sediment. That slow mud is the clock. Measure how thick the mud layer is between two turbidites, and you get an estimate of how much time passed between the two shaking events. Radiocarbon date the microscopic shells inside it, and you can anchor that estimate to a calendar. Do it in a dozen canyons at once, and check whether the pattern lines up. That is what turns a pile of sediment into a chronology. The other thing this record tells you is why magnitude depends on geography. A subduction earthquake gets its size from how much fault surface breaks and how far it slips. Rupture the whole 600 plus miles of Cascadia with tens of feet of slip, and you are in magnitude 9 to 9.2 territory. Rupture only the southern 200 to 300 miles, and you get something in the low to mid magnitude 8 range. And people hear that and assume it is a much smaller problem. It is not a small problem. It is a different problem. Remember that the magnitude scale is logarithmic. Each full step up represents roughly 32 times more energy released. So a 9.1 truly is enormously larger than an 8.1 in total energy. But total energy is not what destroys a house. What destroys a house is how hard the ground moves underneath it, how long the shaking lasts, and how close you happen to be standing to the part of the fault that broke. If the southern segment ruptures, the energy released is far smaller. But it is all released right there, immediately offshore of Humboldt and Del Norte and Curry counties. For the people standing on that coast, the difference between a distant 9 and a nearby 8 narrows dramatically. There is a second thing that changes, and it is the one engineers care about most: duration. A magnitude 7 crustal earthquake might shake for 10 or 15 seconds. A great subduction earthquake shakes for minutes, and structures do not fail on the first jolt. They fail on the 50th, the 100th, after the connections have worked loose and the soil beneath them has started to behave less like ground and more like liquid. Saturated sandy soils along river deltas and reclaimed waterfronts can lose their strength entirely under sustained shaking, a process called liquefaction. And when that happens, the buildings above them do not topple so much as sink and tilt. Portland's industrial river frontage, much of the fuel storage for the entire region, sits on exactly that kind of ground. Even a partial rupture puts a long duration of shaking into the southern coast, long enough for the second and third stage failures that short earthquakes never reach. And then there is the water. The reason a magnitude 9.1 is the number people fixate on is that we have watched one. On March 11th, 2011, the Tohoku earthquake off northeastern Japan registered magnitude 9.1 and produced a tsunami that killed close to 20,000 people. Japan is the most earthquake-prepared nation on Earth. It had seawalls, drilled evacuation routes, a seismic warning network with no equal, and buildings engineered specifically for this. And it still lost that many lives because the wave overtopped defenses built for a smaller event and arrived at some points in under 30 minutes. Cascadia is the closest structural mirror to that fault anywhere in the world. Same style of megathrust, same locked interface, comparable convergence rate, and the offshore fault sits roughly 70 to 100 miles from shore. In a full margin rupture, models put 4 to 6 minutes of shaking across a region stretching from Sacramento to Vancouver, followed by a tsunami reaching the nearest shorelines in 15 to 30 minutes, with modeled wave heights on the outer coast in the range of 20 to 40 feet, depending on local seafloor shape and how bays and river mouths funnel the water. The difference between Japan in 2011 and the Pacific Northwest is not luck. It is investment, preparation, and physics. And on 2 of those 3, that coast is behind. Now hold that next to the southern segment scenario. A rupture confined to the southern margin does not produce 4 to 6 minutes of shaking in Seattle. What it produces is intense shaking on a stretch of coastline where the fault is closest to shore, where a tsunami has the shortest possible distance to travel, and where the road network is thinnest. Humboldt County is connected to the rest of California by a small number of highways that cross unstable, landslide-prone terrain. Crescent City, just up the coast, is the most tsunami-damaged town in the continental United States, struck repeatedly through the 20th century, including in 1964 when a wave generated by the Great Alaska Earthquake, thousands of miles away, killed 11 people there. And this region has already given us a preview. On April 25, 1992, a magnitude 7.2 earthquake struck near Petrolia at the very southern end of the Cascadia Zone. It lasted about 9 seconds. It produced violent shaking, some of the highest ground accelerations ever recorded in North America at that time, and injured somewhere between roughly 100 and 350 people. It generated a small tsunami recorded on tide gauges up and down the coast. Many researchers interpret it as a rupture of a small piece of the Cascadia Megathrust itself, which would make it the only such event ever captured on modern instruments. 9 seconds, a tiny fraction of the fault. So what are scientists actually watching now, and what would have to happen for the worst case? The first thing they are watching is the probability math, and this is where the story has quietly shifted. Time-dependent recurrence modeling published in 2025 puts the chance of a magnitude 9 class, margin-wide Cascadia earthquake at roughly 15% in the next 50 years. That is the number that gets quoted in headlines. But the same modeling puts the chance of a magnitude 8 or greater earthquake in southern Cascadia specifically at roughly 30% over that same 50 years. Double. Some segmented analyses of the turbidite record run higher still for the southern margin, and failure analysis on that record suggests that by the year 2060, the southern margin will have exceeded around 85% of the recurrence intervals recorded across the entire Holocene, while the northern margin will have exceeded only about 27% of its own. The second thing they are watching is the sediment record itself, because it is genuinely contested, and you deserve to know that. Not every scientist accepts that all 22 of those thinner southern beds represent earthquakes. Turbidity currents can also be triggered by major storms, by river floods dumping sediment onto an already unstable slope, or by ordinary slope failure with no shaking at all. If some fraction of those southern beds are not earthquakes, the 240-year figure gets longer. One modeling study of the most likely partial rupture geometries came out with a combined recurrence closer to 530 years. This disagreement is exactly why the 2026 Science Advances team went down with autonomous vehicles and high-resolution bathymetry to map the actual failure scars on the slopes and test, physically, whether those beds came from the sources the earthquake interpretation requires. Scientists generally do not consider this question settled, and no one in this field is claiming it is. It is worth knowing what the planners themselves have already put on paper. A joint state and federal planning exercise for a full Cascadia rupture modeled roughly 14,000 fatalities, 100,000 injuries, and the collapse of around 620,000 buildings. It projected damage across some 16,000 miles of highway, 6,000 miles of railway, 700 port facilities, and 100 airports. Those are not campaign numbers written to frighten anyone. They are the working assumptions that emergency managers in 3 states use to decide how much water, fuel, and medical capacity has to be staged in advance, because the honest expectation is that outside help cannot reach the coast quickly. When the highways crack and the bridges come down, the coastal towns are on their own, and the current planning guidance for residents of that coastline is 2 weeks of self-sufficiency, not 3 days. Third, they are watching the coastline itself sink. Research published in the Proceedings of the National Academy of Sciences found that a Cascadia earthquake of magnitude 8 or greater would drop the coast suddenly by roughly 1.6 to 6.5 feet, not over decades, in seconds. In the worst modeled cases, that would more than double the number of residents, buildings, and roads sitting inside the flood zone permanently, long after the water from the tsunami has drained back out. And fourth, they are watching what else might go with it. A study published in the journal Geophysics presented evidence that a Cascadia Megathrust rupture may have historically triggered large earthquakes on the northern San Andreas, possibly within minutes or hours. The researchers found no evidence of the reverse, San Andreas quakes setting off Cascadia. But in that direction, the coupling appears to be real. Keep an eye on the instrumentation, too. Shake Alert now covers the west coast and can deliver seconds of warning before the shaking arrives. Oregon's Geology agency maintains some of the most detailed tsunami inundation mapping in the world, and vertical evacuation structures, buildings engineered to be climbed rather than fled, have started going up in the most exposed towns. So let us resolve the question we opened with, honestly. A magnitude 9.1 full margin. Cascadia earthquake is not overdue. That word gets used constantly, and it is wrong. 326 years have passed against a full margin average of roughly 500, which means the fault is somewhere around 2/3 of the way through a typical cycle, and those cycles have historically varied from about 200 years to well over 600. A fault is not a train schedule. Nobody at any agency in any country can tell you the year. Scientists cannot accurately predict earthquakes, and anyone who tells you otherwise is selling something. But the most realistic danger here was never the number in the headline. It is not the margin-wide event with the biggest magnitude and the longest odds. It is the shorter rupture at the southern end of the fault, the one with roughly double the probability over the next 50 years, sitting closest to shore on the least populated and least prepared stretch of that entire coastline, where the wave has the shortest possible distance to travel and the roads out are the fewest. It would not make the same magnitude number. It would not need to. It would simply arrive with the least warning in the place least ready for it. That is the earthquake the sediment is pointing at, and it is the one almost nobody is talking about. So tell me in the comments, have you ever felt an earthquake strong enough that you had to grab onto something? Where were you and what did it feel like? I read these. If this was worth your time, hit that thumbs up. We are going for 5,000 likes on this one. Subscribe so you are first to know when something major happens. Let us go. See you in the next one.